Hello guys and girls, and welcome to the Printerview, a PLM group hosted webinar on 3D printing. With us here today we have Wester. Welcome, Christopher.
Thank you, Matthias.
Christopher Wester is one of PLM Group's many 3D printing experts, and he is here today to guide us through some of the most common applications that you can 3D print. So without further ado, Christopher, would you please guide us through this webinar?
Yes, of course, Matthias.
Excellent.
So I will guide you through some of the most common applications that we see when we are out in the industry visiting customers. And I will start with you can just click there.
Yes.
I will start with the product life cycle, and then starting from that, I will guide you through some of the most common applications. So what you see here is a common product life cycle. So in the beginning of a product's life cycle, you have this design phase, usually in quite low volumes, producing volumes. Then that is followed by usually a tooling phase where production is ramped up a little bit and volumes are a bit higher. Then there is quite a long production phase, and the product is launched and on the market.
Yeah.
Following that is a spare parts period where volumes are usually lower. And this is a normal curve that products usually follow. And starting from that, we can see that 3D printing or additive manufacturing can be used throughout the entire product life cycle. In the first step, we have what's called rapid prototyping. This has been used for as long as 3D printing has been around, since the 1980s. In tooling, it's what's called rapid tooling. It's also been around for a long time now, since the 1990s.
Right.
Following that is rapid production for high volumes, of course. And following that is something that is ongoing right now. It has been implemented, but it's still coming more and more. And that is print on demand,
Right.
which has to do with spare parts. So I will take a few examples from each of these categories and then discuss, what has been done so far and what can be done.
Brilliant. Let's do it.
Okay, so we'll start with rapid prototyping, or the design phase, where we can use 3D printing. So, and this has been used for, as I said, since the 80s. It's been around for a very long time. Yeah. And I think most people listening already know what can be done with 3D printing in this area. I mean, to print something is usually faster and cheaper than doing it by hand or outsourcing it to a machine shop, for instance. But I have a few examples for you to see that illustrates that. The most common challenges that we see out in the industry when it comes to prototyping is, first of all, lead time. Outsourcing to a machine shop usually takes several weeks, 2, 3, 4, 5 weeks to get the parts in-house.
Right.
And during that time, you can't do anything else in terms of product development. You need to wait for the prototype.
So no design changes, no iterations.
No, exactly, yeah.
Right.
So you're locked for several weeks.
Yeah.
And if you can do that print within, let's say, a day, that really helps in bringing the product to market faster.
Of course.
The second issue we see, or challenge in the prototyping phase, is that it's quite expensive to order one-offs. It takes machine time. And by doing it by hand is even more expensive.
Yeah,
of course. So digging deeper into some of some examples that we have. So this is a part that used to be machined, drilled, welded, treated in aluminium, I believe.
Right. So lots of sub-processes.
Yeah, exactly. Yeah. So this part is now today printed in nylon and then reinforced with Kevlar to make it strong. And comparing traditional manufacturing to 3D printing sees quite a big reduction in lead time.
Yeah.
So lead time is down to 62%.
Great.
And that in and of itself is quite good. But looking at the cost to produce this aluminium compared to 3D printing it, well, you have the numbers there. So 2,600 euros for one part, and to print it is 54 euros.
Yeah, that's a huge difference.
Yeah.
Right there.
So this is a really good example on bringing prototypes, functional testing in-house really cheap.
Yeah.
And also reducing lead time.
Yeah.
So this is something we see all across the board. Everyone who uses 3D printing for prototyping sees these numbers. Speed is also important, of course. So this is one of the latest machines from 3D Systems called the Figure 4.
Yeah.
What's unique about this is the printing speed. So this is printed from a liquid, and it can print 100 millimeters per hour. And on top of that, it has a really super high resolution. So this is just one example of a part. If you can show this to the screen.
Show this to you. Continue.
So if you look at the top there, for instance, you can really see, if we can get it into focus.
Yeah, there we are.
The kind of surface you get from these type of machines. See, it focuses on meat steel. I should hide behind here.
Let's see if we can get some. There we are.
Yeah. So I mean, injection molded quality at 100 millimeters per hour.
That's fantastic.
Yeah. So this part, it takes about an hour to print, and I think you even print 4 or 6 at the same time.
Right.
So to have these fast iteration cycles in-house to produce prototypes, save time and money, it's outstanding. So this is new technology, really impressive. And I mean, using this for prototyping has been done for a long time, so I think most people already know. If you have a engineering department, I mean, designers, whatever, that uses prototyping, 3D printing instead.
Excellent.
Yeah. So the next sort of phase in the product design life cycle is
the curve you showed.
The curve in the beginning.
Yeah.
So we've now left the prototyping step, so to speak, and going into tooling. So tooling is growing more and more, I would say. The most common challenges we see in this area when we're out talking to customers is, first of all, lead time. Depending on which industry you're in, let's say if you're working with injection molding,
yeah,
I mean, tools can take 6, 8, 12 weeks to get in-house before you can start actually producing parts.
Both production and shipping, of course, of the tool.
Yeah, many companies today use China for manufacturing of tools.
Right.
But I mean, it's still several weeks, no matter what type of tool you're ordering.
Yeah.
That also ties into cost. Tools are almost, it requires a lot of, you steal machine time. Setting up a machine just to produce one part, you steal machine time. Yeah. Even if you do it in-house. Yeah. You like occupy a machine just to produce one part.
Of course.
And also, some parts requires, or you would like to have extra functionality or complexity, cooling channels or whatever inside the tool, but that comes at an extra cost.
Yeah.
And not everyone is willing to actually apply it. Right. So they don't do it. So right. they get a tool with potentially lower production
quality,
right. Yeah. Capacity is lower,
and that may affect, of course, the end use product.
Yeah, of course. Yeah. So this is just some of the things we see when we talk about tooling with our customers. Some examples, some recent examples. This is borderline prototyping and tooling. So this is actually a low volume tool used for injection molding. So what we've done here is we've printed a plastic tool that would then use for injection molding to inject plastic into.
Right.
And since it's in plastic, you can't use it for as many shots as you do for steel tools, of course, or aluminium tools. So this is the actual tool that we've printed. So what you do with the tool then is that you put it inside a mother tool.
Yeah.
And then you inject plastic into it. So why would you want to do this? Why don't you just do steel tooling? Well, this is mainly if you have really low production, like a few hundred parts, or if you want to use it for prototyping. So this was printed on a 3D Systems machine. We did it for a Danish company called SPT Wilecon, and they wanted 200 parts, and no one in the injection molding industry would take these kind of jobs. It's too expensive to make a tool just to produce 200 parts. So we did this in plastic. The tool cost was roughly 500 euros, just below 500 euros.
Yeah, that's the printing cost.
The printing cost, yes. The print time was 20 hours.
Okay.
And we managed to get 200 shots out of it. They only required 200. We actually managed to get some extra shots out of it. But to be able to get a functioning injection molding tool in less than 24 hours for 500 euros, that's impressive.
Bordering on unique.
Yeah, exactly.
Right.
So this can be used both for prototyping when you require the part to actually be injection molded.
Yeah.
You don't want to print it, you don't want to mill it, you don't want to do anything else. And it's really fast and really cheap. Then you can, of course, use a steel tool once you do the design of the tool.
Of course.
Or if you have really low volume production. Next up is an actual metal tool. So this is used for metal forming, stamping. So what we did was that we printed the entire tool.
Mm-hmm.
We put it inside a stamping machine, and it's run since then, basically.
Oh.
So what we did was we compared the lead time of the tool, the cost, the weight, and the hardness of the tool.
Yeah.
So these are the numbers we got. So lead time of the actual tool was reduced by more than 50%, which in itself, this was for the car industry, and that is huge to be able to get the tooling done faster. Cost of the tool was actually a little bit higher, 5 to 10% higher than using traditional manufacturing.
Right.
But this was compensated by the reduced lead time in this case. The weight of the tool was also reduced by almost 50%, I think 40%.
Yeah.
And that enables you to actually run the tool faster.
Right.
So you consume less energy and you can use, stamp faster with it.
And therefore you can increase your production time, right?
Yeah, exactly.
Yeah. Okay.
Yeah. So lots of benefits. And also in this case, it was really important to have a high enough hardness. And we managed to, after hardening, get the same hardness as for traditional tooling.
Brilliant.
So this is an excellent example on how to use, real tools for real applications for high volume production.
Yeah. Yeah.
Another example when it comes to tooling, that is fixtures. And this is also a really, really common application. We have, hundreds of examples of this. And I would say these are the two most common applications. Prototyping, rapid prototyping, and fixtures.
I think most of us can agree on that,
exactly.
and definitely anyone in the manufacturing.
Yeah, exactly.
Yeah.
So most people have probably seen this before. I just ran some numbers through our system. This is the average over our 3D printing customers. So, so the fixture you can see here is a fixture for a
bring that up to the screen.
Yeah. And this is to replace, machined fixtures. To machine a single fixture is time-consuming, expensive. It takes machine time to do.
Yeah.
And on average, lead time would be reduced by 90% and cost by roughly 70%. That is the numbers we see all the time. Sometimes it's even better than that.
Right.
Some other just quick examples. Fixtures is real common, so it's good to see what it has been used for. So this is, of course, you can use standard parts for your fixtures. So this is used to fixate this part.
Show this as well.
And to be able to produce these parts, the same day that you design them, put them in a production line or an assembly line or in your measuring machine for, basically no cost at all. That's a huge benefit.
So you can go from idea to 3D printed fixture in less than 24 hours.
Yeah, I would say so. Yeah, depending on the size of the part, of course, but sometimes it's like 4 hours, sometimes it's 30 hours, but it depends on the size of the part.
Right.
So if you don't use this already, start using it. It's a no-brainer. You would save time and money by printing your fixtures.
Brilliant.
Yeah. On the same note is grippers. Usually robotic grippers.
Oh yeah, for robot cells production.
Yeah. Picking stuff up from other machines and putting into other machines. So all types of automation, really, robotics. So this is a pneumatic gripper that has been printed in one part.
Yeah.
So the first benefit is that you actually reduce the weight by quite a bit, and this is something that would move something. So having a lightweight gripper is really valuable. So this went from almost 2 kilos to 200 grams, which is a huge benefit in and of itself.
Oh yes. Yeah.
You also consolidated a lot of parts into one part. So instead of assembling the gripper with like tubes and valves, and because this is a vacuum inside,
which takes time and costs money, and there needs to be some kind of manual labor to assembly. Yeah.
So all of this was so the amount of parts was reduced by 80%.
Oh wow.
So even though this is not the actual gripper, this is just something produced on the same type of machine. So this is from HP's multi-jet fusion machine.
Yeah.
Just goes to show the complexity. You can print the material qualities. You can feel it. So this can go straight into production.
Excellent. Let's see if I can show that a bit close up of that.
So this is actually a drone body, but it goes to show again the resolution, complexity, and the material quality you get out of these machines today.
Of course, yeah. Brilliant, thank you.
And just to be able to print your, let's say, robotic grips instead of milling them, also saves a huge amount of cost and time in the same numbers as the previous slide when it comes to fixtures, jigs. Yeah. Okay, so that's lots to say about tooling and fixtures and jigs. Excellent applications.
And it's still a growing area, of course.
Yes, it is.
Tooling, jigs and fixtures, and tools for injection molding.
Yeah,
we should mention. Yeah,
and also since automation is growing quite rapidly.
Yeah,
I mean robotics in general. Yeah. To be able to print grips or even the robot itself, you can print today. Okay, so last up is the production step. And people, I believe, when I'm out talking to customers, believe that 3D printing is only used for rapid prototyping, for prototypes, low volume production, jigs and fixtures, but that is actually not the case anymore.
Right.
It can be and is implemented on a much wider scale in production.
Yeah.
So these are just some examples on how to do that. But first, I would like to talk about when to use this, because it's not always suitable. You shouldn't always print in the same way as sometimes you mill, sometimes you turn, sometimes you drill, sometimes you injection mold.
So what you're saying is 3D printing is not a replacement technology for other more traditional manufacturing methods?
No, it's more of a complementary technology.
Right.
Yeah. So all of you with CNC machines out there, do not fear.
That's good. I'll be comforted. Yes, sorry.
So the challenges we see in production today is that low volume production is usually quite costly, and therefore it's usually rejected or turned down. So if someone comes to you and say, can you injection mold 2 of these?
Yeah.
No.
Right.
I mean, for machining, you can do it, but it's usually quite expensive. So sometimes, or a lot of times, these jobs are turned down.
Yeah.
And also part complexity costs extra, which is not the case for additive manufacturing. And since complexity costs extra, you usually go the simple route and design the parts so that it's easy to machine, which might reduce functionality.
Yeah.
And that is something, again, that 3D printing or additive manufacturing can remedy.
Yeah, that's one of the benefits of 3D printing, of course. Complexity is free.
Complexity is free, yeah. So when to use additive manufacturing? So this is just a simple schematic on when to use it. So manufacturing cost is on the y-axis.
Yeah.
And on the x-axis, you have the amount of material that is removed versus how much is added. So for subtractive manufacturing, or that is machining, milling, and turning, and drilling,
where you actually subtract or remove material from like a block of, I don't know, titanium or whatever.
So you buy a block of titanium, you mill away 80%, and you have your part.
Yeah.
So the cost with the amount of material that you actually remove.
Right.
Right.
Yeah.
That includes. That is, more machine time and more material goes to waste.
Yeah.
While additive manufacturing goes the other way. So the more amount of material you have to add, the more expensive it gets. And there is some kind of balance there.
A breaking point.
A breaking point, yeah. So sometimes you want to mill, sometimes you want to print.
Yeah.
So there is no clear answer on when. So a good example is like a big ring. A ring. If you want to machine this, you have to buy a big chunk of aluminium, mill away 90%. For additive manufacturing, you just print the ring. Right. Which is much cheaper.
And that's it.
Yeah. On the other hand, if you have a brick with a hole in it, it's easier to just drill it than to print the entire structure.
Right. Of course.
Exactly. And there is a graph when it comes to injection molding. So when do you want to injection mold something, and when do you want to print it directly?
Yeah.
So if you look at additive manufacturing, the cost per part starts at 0. Then you print 1, 2, 3, 4. So goes up linearly, right?
Because you have no previous tooling costs, etc.
Yeah. So you start at 0, and then each part is more expensive than injection molding. Whereas if you have injection molding, so then you need to buy a tool. So you have a high initial cost.
Yeah.
But then the cost per part is lower, of course.
Yes.
So then you have this intersection here. So this intersection has moved throughout the years.
Right.
So
how do you mean moved?
So from the beginning, maybe you could print, I don't know, 100 parts.
Yeah.
Then it was, because they were so expensive. Before that, you had to buy a tool, to make a tool.
Exactly.
Then it was maybe 1,000, and this has continuously moved, right? So the cost per part to print has gone down quite a bit.
Is there like an industry average for the number of parts you can print before, It
has to do with the technology that you print with.
The 3D printing technology, the cost of the materials.
Yeah, exactly.
Right.
Yeah.
Right.
So this for the highest capacity printers today, this number has actually moved up to 110,000 parts.
Oh wow!
So anything below that, and this is for smaller parts. So this case was done with this small wheel. You can show this.
Of course.
So this part was printed on again on the HP multi-jet fusion machine, and you compared the cost of a tool, and then you started printing it, and you did this intersection. So if you're a company that produces parts in this size, if it's less than 100,000 or 100,000, it's just cheaper, straight up cheaper to print it. No need for a tool.
Wow.
And I mean, if it's 10,000 parts, it's no question.
Right.
Or 50,000 parts. Yeah. So this number has actually increased quite a bit, and is increasing even more. So I mean, there's still need for tooling when it's like millions of parts.
Of course. Yeah.
But I mean, it's getting there.
So it's something to keep track of if you're in manufacturing?
Yeah.
Right. Excellent. Thank you.
So that is some guidelines on when to use it when it comes to machining and injection molding.
Sorry, here we go.
So when it comes to something that's really important when it comes to additive manufacturing and production is designing for additive manufacturing, because that reduces material waste, it reduces weight, you can add complexity, blah, blah, blah. It's big on its own, so I will just touch it briefly.
Maybe we could do that in an upcoming webinar.
Yeah, so if you would like that, let us know.
Yeah, please do.
So this is just a quick example on what HP prints for their own printers. So this is a part that used to be machined in aluminium. So you can see the aluminium part there.
Yeah.
And then it was like a three-step rocket to design the part. So the first step was to print the same part using a 3D printer instead of machining it. And I mean, that works. But then you realize that, I mean, it's designed this way to be machined. But what if we redesign it in another way? So then they did the black part up to the right.
Yeah.
With holes in it to reduce the weight, and that worked just fine.
Right.
And then the third step was to actually design it to be printed from the beginning. So that is the gray part at the bottom right. It has this sort of organic shape.
Yeah.
So that is optimized to print, to have the optimum functionality and reduce the weight, and of course reduce the cost as much as possible. So this is an excellent example on how to go from machining to an optimized part using additive manufacturing. So if we compare the weight of a CNC'd or a machine part compared to a printed part, it goes from 350 grams to 20 grams.
That's impressive.
Yeah, and this is actually something that is moving inside the machine. So this reduces wear and consumes less energy, of course.
Yeah.
And the cost was reduced by 50%.
Wow.
So this is really impressive.
Yeah. And you're saying this is a part that is actually in some of some of HP's 3D printers?
It's actually for the 2D printers. It's printed on a 3D printer, but it's used in the 2D printer.
That's nice. That's nice. Yeah.
But the 3D printer itself has a couple of hundred printed parts.
Okay. Yeah.
So this is something to keep in mind, even though it's not maybe the first step when buying a printer, but this is something to keep in mind that, I mean, the benefits can be exponentially sort of.
Right. Right.
This is another good example on a product that is designed to be printed. So from the bottom up, so this is a 7-axis robot. Everything is printed except for electronics and stuff, of course. It was designed to be printed. So like all angles, thicknesses, no, the entire design is made to be printed. So this is done with a Markforged 3D printer that prints in a continuous carbon fiber to make the robot light and strong. So this is, just to illustrate, this is the inside of such a part, where you can see the actual continuous carbon fiber that strengthens the part up to the strength of aluminium.
Show that, I suppose. Yeah, it's right there in the middle, right?
Yeah, the sort of shiny bit is continuous carbon fiber.
Right.
Yeah. And again, this makes the part as strong as aluminium.
Yeah.
So instead of machining the outside and the inside and the parts for this robot, everything was printed.
Of course, because obviously the robot needs to withstand some forces, right?
Yeah, exactly. And it needs to be able to lift a certain weight and stuff.
Yeah.
So the cost was reduced by almost 60% to produce this part instead of machining it. Lead time to produce one of these robots went from 30 days to 9 days, which is also really impressive.
Yeah.
But what's even more impressive is that because they designed it to be printed, they could again consolidate many parts into one instead of having to assemble them.
Right.
And for the entire assembly of the robot, they went from 800 parts to parts. You can imagine the amount of like work to put it together.
And time.
And time, yes, of course. But also in terms of like service, there are less screws and stuff that keeps stuff together.
Parts that can break in the wear and tear, right? Yeah.
So everything is consolidated into one. So this is also a great example of when additive manufacturing is used in production. I mean, it's not I don't know how many of these robots they sell, but it's still in their full production.
Yeah.
Another good example, and this is on a metal machine. That's a Markforged Metal X machine. Another part that was designed to be printed. So this is an actuator housing for an outdoor tool.
Yeah.
And so this needs to be very resistant to stresses, of course, to wear and fatigue, but also be lightweight. So this part used to be machined and assembled from 4 different parts.
4 different parts, yeah.
4 different parts. It's now been redesigned as one part. It's been thoroughly tested, so this is suitable for the actual application, for a real outdoor tool.
Yeah.
The company is Stanley Black & Decker, who designed the part and the machine.
A well-known international brand.
Yeah, I would say so. So the numbers you see here, so the costs went down to 59% and lead time to 31%. And these numbers are for serial production.
Serial production.
Yeah. Right. So the entire range of these products that need to be produced within a year, these are the numbers compared to machining.
Wow.
If you would use this for prototyping, so if you only needed one of these parts, it will be 95% reduction in both lead time and cost.
Wow. Right.
So that's really impressive.
Yeah, it is.
And on top of that, the weight of the part was reduced by 50%, 53% even. And this is, again, is an outdoor tool, so weight is really important.
Yeah, of course. Yeah.
So, I mean, using additive manufacturing in production, it doesn't need to mean 100,000 parts. In this case, it's maybe a few hundred.
Yeah.
But it can be used.
Yeah, so definitely applicable. And I suppose, according to the latest figures from some of the global reports, using 3D printing technology for producing end-use parts is one of the fastest growing areas, right?
Yes, that's correct.
Yeah. Excellent.
So, and that was it. That was the 3 main areas. I skipped the spare parts. I think that's coming more and more, so I don't have any really good examples of that right now. But so what you've seen now is that additive manufacturing can be used in both prototyping and design, tooling, and production in many areas. This is just a few, the most common ones we see.
Yeah.
And if you don't use it already, especially for rapid prototyping or fixtures and jigs, just do it.
Just do it.
Just do it.
Excellent.
Yeah.
And on that note, I'd like to say thank you very much for coming, Christopher.
Thank you.
And looking forward to seeing you soon again, both you, the audience, and Christopher, of course. And thank you very much for watching. See you around.
Bye.
Bye.